All right. So this is one of the applications of frictional force. A car can move along a curved road like this. We want to calculate the maximum speed required by this car to move along this curved road without any form of skidding. In that case, this car has a weight that acts vertically downward, and that is mg. It has a normal reaction, which is r, or if we like, we can call it n, so that it won't be the same as the radius of the curved road. There is a frictional force acting this way, and we call it F of S. So, what provides the force required for this body, for the car to move along the curve without skidding? So, that force is called frictional force. And it has been already established that force is equal to mv square over r, if r is the radius of the road. Since frictional force is providing this force will be changed to F of S is equal to mv square over r. So what is frictional force here? The frictional force here is mu s r, which is equal to mv square over r. What is r? There is no motion along this direction. As a result of this, n is equal to mg. But don't forget here that n is the normal reaction here, while r here is the radius of the curved road. So instead of using mu sr here, we will rather use mu sn. So according to this first diagram, what is n? N is equal to mg. As a result of that, we have mu s mg is equal to mv square over r. Alright, so mass will cancel mass, and we have mu s rg is equal to v square. So from here now, we can calculate the value of v. V is equal to square root mu s rg, and this v is the maximum speed with which a body moving along a curved road can move without skidding. We can put any value here and we get the maximum speed with this formula. Alright, now let's look at another one, because we have two types here. Here we have a flat road. In the other one I want to discuss about a banked road. So let's look at another one. So this is a banked road. The body is like this. This is weight mg, and this is a normal reaction, which is r, and then this is angle theta. When we resolve this r here, we have r cos theta, and when we resolve it here, we have r sin theta. Again, along this curve, we will still calculate the maximum speed required for a body to move along this curve without skidding. So, but there is now a difference. What is the difference? The difference is that here the road is banked. In the previous one, we had a flat road. All right. So let's now move on. F is equal to mv square over R. What provides the frictional force here is R sine theta. But my R here again, I will change it to be N so that there is no confusion between normal reaction and the radius. So I have N here as well. So we have N sine theta equals mv square over R. N sine theta is equal to mv square over R. Along this line, vertically like this, there is no any motion. So we have N cos theta, we have N cos theta is equal to mg. If we call this equation 1 and we call this equation 2, if we divide equation 1 by equation 2, we have sin theta over cos theta, and that will give us tan theta. If we divide this by this, m will cancel this, and we are going to have v square over rg. V square over rg. Cross multiplication from here will give me rg tan theta is equal to v square. Find the square root of both sides. We have v is equal to square root rg tan theta. This is the maximum speed required by a body to avoid skidding along a curved road. Now, let us try to play with some values. If our radius is something and we put our theta to be something as well, what is likely to be our maximum speed required? Let the radius be something like 100 meter. And of course, g is equal to 10 meter per second square. And let my theta be 45 degree. So we calculate maximum speed thus equals to square root rg tan theta, and this will give me square root, what is the radius? 100, or let me make it, okay, 100 is okay, multiply by 10, then times tan 45 degree, if my angle is 45 degree. So as a result of this, I have square root 1000 multiplied by tan 45 degree is 1. So I have square root 1000. So this will give me